welcome to a new week. Welcome to Kinetic Energy. Welcome to my continued efforts to sound more enthusiastic while recording these videos, and my continued efforts to find it quite difficult. So Kinetic Energy carries on from where we left off last lesson. Very similar topic, and it's something that we'll revisit plenty in year 11. So if you find it a little bit difficult this time around, don't worry too much. Plenty of time to practice going forward. First question then, state the equation for gravitational potential energy. This is what we looked at last lesson. Good. Remember, again, all these questions make up the start of your assessment, so it might be good to have that open in a separate tab, separate page, so that you can be answering as you go along, or indeed cheating and when we get to the answers. 2. A mug with a mass of 0.2 kilograms is on Earth. How much does it weigh? This is going back a lesson before, thinking of that equation that links weight, mass and gravity. 3. State Newton's second law. You can either go for the wordy version of this or the simpler one, which is just the equation. 4. Is this reaction reduction or oxidation? So look what's happening to the electrons and whether they are being added or lost. Remembering oil rig is your way of reminding yourself of that. 5. What is meant by the activation energy of a reaction? So those profiles there might be helpful in reminding you of that. You give a nice little definition for that. And then finally, state the word equation for photosynthesis. This is a really important thing to make sure that is still in your mind, forefront of your mind. You'll need it lots and lots for your GCSEs, particularly your biology ones. Okay then, go through the answers. So gravitational potential energy is dependent on the mass, the height and the gravitational field strength, which is gravity. Your mug was on Earth, so that gravitational field strength is 10. 0.2 kilograms times by 10 is 2 newtons. Weight is measured in newtons in this way. Force is mass times acceleration. It gained electrons, so we call that reduction. Remember, oil rig, oxidation is loss, reduction is gain. Activation energy is the minimum energy required to start a reaction. And then photosynthesis, you take water, or plants take water, they take carbon dioxide and they make oxygen and glucose. You remember that the opposite of this equation is respiration. So a nice way to remember those two important equations at once. So we are looking at kinetic energy today and energy transfer calculations. They go together because it very much follows on from gravitational potential energy, as I mentioned earlier. So the lesson's kind of in two parts. First, we'll start by stating the equation for kinetic energy and doing some calculations, and then we'll look at this energy transfer and how kinetic energy and gravitational potential energy link together. Good. So just to remind you all of what we looked at last time, which was when we move an object higher, when we take it higher into the air, we increase the height, we give it more gravitational potential energy, because an object's potential energy is dependent on its mass, its height and gravity. Gravity will be fixed to the planet that it's on. Its mass is fixed to that particular object, but height we can move around. The higher the object is, the more gravitational potential energy that it will have. Okay. Now, when objects fall, that potential energy, that gravitational potential energy, turns into something else. So if you think of that object sat on the edge of a height preparing to fall, it only has potential energy until it begins to fall. When it falls, that energy is turned into movement, And that movement energy, we give a special name in physics. We call it kinetic energy. So my Simpsons clip here, at the top has gravitational potential energy, and then it's converted into kinetic energy as he falls. Okay, and we have an equation for kinetic energy in much the same way that we had for gravitational potential energy. This again is one that we need to learn. It's a slightly trickier one, but it's very doable. And it is this here. Kinetic energy is equal to 1/2 or 0.5 times by the mass of the object times by the speed of the object squared. Okay, and this is your triangle for it. This is one of the trickier equations, and it's important that we can learn it and we're able to use it. If you think about having been hit by an object that is thrown, or hit by a car, or hit by anything that's moving, really, this equation makes a lot more sense. The amount of energy that you're hit with, i.e. the amount that it hurts, really depends on the mass of that object and the speed of that object. And speed is much more important. If you think of a bullet, it hasn't got much mass at all, but because it's going so fast, it's got enough energy to kill you. Whereas something with lots of mass, think of a sofa, if it's not travelling very fast at all, it doesn't hurt that much at all, does it? If someone's able to, if you bump into a sofa or a sofa falls towards you, it's not anywhere near as painful as an object with less mass travelling much faster. Same way, if anyone's ever chucked a pound coin at you or a penny at you, if you get it fast enough, it really hurts. Okay, so we'll look at a couple of examples of this, 1, 2, and an exam question. I'll do that on paper, and then we will come back to look at the rest of the lesson. Good. So our first example here says a car is travelling at 20 meters per second and has a mass of 1,200 kilograms. What is its kinetic energy? So this is just a case of using our equation that we've just looked at. Kinetic energy equals 1/2 times mass times velocity or speed squared. Velocity and speed are interchangeable in this. And then going through the different terms here. So kinetic energy is what we're trying to work out. So it's a question mark. My mass is 1,200. My velocity or speed is 20. Okay, so then we just put that into my equation at the top here. 1/2 times 1,200 times velocity squared. Okay, and it's good when you're doing this to do it in little bits, so get your calculator, but you didn't think I was cool enough to have my own scientific calculator, did you? 20 squared to start it out, just because sometimes if you put the term like that straight into the calculator you can make mistakes. Then times that by 1,200, then times it by 1/2 or 0.5, and you come out at 2,000 or 240,000 joules of energy, which is a lot of energy, but you'd expect that cars have lots of kinetic energy when they're moving around. If this asked for you the answer in kilojoules, you'd need to divide by 1,000, so you get 240 kilojoules of energy. This up here, sort of a bog standard 2-3 mark question. The important bit is learning this equation and being confident using it. Okay, good. Okay, so this second question is a little bit more complicated, still using the same equation though. It's important with questions like this, learning the equation is always going to be worth at least a mark, so it's really important that you do, and it's really important that you start by stating that equation. I know that's a very repetitive thing to say, but particularly if you don't like physics and you don't like maths, take the easy mark that you get from stating that equation. You get that and then go from there. These questions can be difficult, they can be quite confusing. You're not expected just to know it, it's about working it out, taking a little bit of time working it out. It is definitely, when you answer these questions in a minute, a case of getting a pen and paper and working out each step. Don't expect just to be able to do it because you've watched this video or you've read the lesson. Okay, so kinetic energy, this time it tells you that it travels with this amount of kinetic energy, so we can write that in here. My mass 1,890 and my velocity or my speed is what I'm trying to work out. So if we put that into my equation, we get 76550 is equal to a half times my mass 1,890 times my velocity, my question mark, squared. It's important to remember that we've got that squared term here. And this is nasty looking, and depending on your point of view, you might be of the mind that you're going to do your triangle. You've got kinetic energy at the top, you've got your terms at the bottom, mass, velocity squared, and this is what you're trying to work out. So you need to do kinetic energy divided by a half times by mass. Okay, or you can just look at it and you can work it out step by step, which is what I would do. So my first thing would be to times these two numbers together and write it out again. So you can have 76550 is equal to, we work this out, times by 0.5 is equal to 945 times by my speed, my velocity squared. This is a case of taking your time over it. This would be worth a good 3-4 marks in an exam question. Take a good 3-4 minutes over it. So now I need to get rid of this on both sides, so I'm going to divide by 945. So I'll do 76550 divided by 945 is equal to my velocity squared. Taking your time over it and writing it out this way as well just makes it much more, or much easier to see where mistakes might have crept in. So 7655 divided by is 81.005. There are a few extra numbers there, as you can see, but it's fine just to leave it in your calculator. Don't worry about writing it all out for a minute. And then I need to get rid of this square on both sides, and I do that by square rooting my answer, and my speed comes out at, or my velocity comes out at 9 meters per second. Okay, that's my final answer. In this question, your marks, you would get a mark for stating the equation, you'd get a mark for showing that you know where the numbers go, and then for rearranging it, and your final mark would be this answer. So even if you go wrong somewhere, you will get the vast majority of the marks by approaching it logically and stating what's happening in each one of these stages. So it's worth taking time over it. Okay, good. Okay, so if we look at this exam question, this is exactly how these questions would look like. This was from the 2018 paper. It was in the year 11 mocks, and people answered it reasonably well, although they made one mistake that is easy enough to make. So it says a student models a crumple zone by adding a spring to the front of a toy car. The spring compresses when the toy hits the wall. You don't need to worry about any of that, it's just giving you extra information to make it a little bit more confusing for you. So we can just ignore that really. before the toy car hits the wall, its speed is 2.2 meters per second. The total mass of the car and the spring is 500 grams. Okay, show that the kinetic energy of the toy car and spring is about 1.2 joules. So it tells you kinetic energy, so you should immediately be thinking kinetic energy, a half times mass times speed times velocity squared. And then go through it just as normal. You can say mass is equal to 500 grams, speed is equal to 2.2 meters per second. So the thing that makes this question a little bit trickier is this bit here, is that my speed is in grams and it needs to be in kilograms. We're 1,000 grams in kilograms, so this is 0.5 kilograms. If you don't do that conversion, your answer won't match theirs, and so you won't be able to get all the marks. So then it's just a case of putting it into your equation. Kinetic energy is equal to a half times my mass, 0.5, times my speed, 2.2, remembering to square it. Okay, so stick that into my equation, 0.5 times 0.5, so that's a quarter, 0.25, times by 2.2 squared, 4.84. So my final answer comes out at 1.21 joules, which is pretty much what it asked for in the question up here. Okay, it is worth breaking it down as I did there, because it's very easy to make a mistake when answering this as one big question, because there's lots going on there. If you forgot to convert to 1,000 kilograms, your answer would come out as, you know, a factor of 1,000 off, and you might be able to catch it and work back. So with questions like this where it gives you the answer, give yourself some time, look back through, look for mistakes if it doesn't quite match what is expected, and see if you can work it out from there. Good stuff. Okay, so hopefully you've just seen me going through these questions here, all of which are in your assessment. So if you struggle with any of them, flip back to the video, watch them again, remind yourself of how to do it. So the next part of our lesson is to look at this conversion between gravitational potential energy and kinetic energy. And this is just the idea that when an object begins to fall, it starts to lose gravitational potential energy because its height decreases, but it gains kinetic energy because it will pick up speed as it does that up until it reaches its terminal velocity. And again, this really is a topic that we'll cover again next year. So it's just to introduce it now to make sure that we have an idea of it, and then we'll look at an exam question. So we can start by watching this video here, which shows the highest free fall ever done by man. So this is a helium balloon that takes him up to the edge of our atmosphere. As he goes higher, his gravitational potential energy is increasing. Okay. And this is the key bit here. At the top, he's no longer moving. He's gained maximum gravitational potential energy. And looking down, a very scary sight, he is about to convert that gravitational potential energy into kinetic energy as he starts to fall back to Earth. Absolutely no amount of money would get me up here. Terrifying.
Speed 725. Showing Felix at a stable descent.
Okay. As he falls, his kinetic energy increases until he reaches terminal velocity, which, if we remember from a few lessons ago, is about 120 miles an hour for a human. Even though he's at much, much higher, his maximum speed will still only reach that terminal velocity. It will still be the same. However, there'll be lots more energy created. It will be turned into heat, things like that. All as he falls. The energy's still there. It's just in a different form. If he just kept going, didn't open a parachute, he wouldn't be very well. But that's not what happens. And there he goes. Okay, good. So that video shows how gravitational potential energy can get converted into kinetic energy. There's another more on-Earth example of this. This is how roller coasters work. The reason most roller coasters start with a big climb is they're building up gravitational potential energy, and then you drop down and that's converted into kinetic energy. And it should just be that conversion from gravitational potential energy to kinetic energy that pretty much keeps your roller coaster going throughout the ride. They sometimes cheat a little bit and have a few wheels to keep you going to build your speed up again, but it's basically a conversion of energy from that top height down into kinetic energy that keeps you going. Okay, so this is an exam question about this idea. It says that this is a question about gravitational potential energy and kinetic energy. Look at the diagram and information about a small ball falling from a height of 20 meters. And it shows you some gravitational potential energies getting smaller and some kinetic energies getting bigger. And it says, explain the changes and describe what would happen if the mass of the ball was doubled. Use equations to help explain your answer. So this is a 6-mark question. It's a particularly tough 6-mark question. We'll go through the answer together. The key thing to realise is the question's guiding you a little bit here. It's saying use equations to help explain your answer. So this is why it's really important to make sure you know these equations, because your first 2 marks are going to come from stating them. Stating the equation for kinetic energy, which I've got here already because we've done it today. And then your second equation, which is that for gravitational potential energy, which is this here. So if nothing else with this question, you get a couple of marks from stating those 2 equations, and 2 out of 6 is perfectly good when you come to a really tough 6-mark question like this. Your next mark can be to explain the changes, which really what it's looking for you to talk about is this idea that gravitational potential energy is getting smaller and that kinetic energy is getting greater. And that's because your gravitational energy is being converted into kinetic energy. So we can say that here. You're showing that you understand that that energy is not disappearing, it's being converted into kinetic energy. And if you add up any of these numbers, they will always come to that original 100 value because the energy is still there, it's just being moved. The next bit, the tough bit, is to describe what would happen if the mass of the ball was doubled. And there's a few ways you can go about this. The way that I've done it here is to calculate the mass of the ball in the first instance. So we can say we've got 100 joules of gravitational potential energy. my ball is at a height 20, and gravity on Earth is 10, and we can use that to find out the mass of the ball by first of all timesing 20 by 10, and then doing 100 divided by 200 to find that my mass is 0.5 kilograms. And if we think then, if I double that mass, if I made it 1, my gravitational potential energy would double. Okay, so doubling this mass would also double the gravitational potential energy. And if I've changed my gravitational potential energy, if I made that 200, well then my kinetic energy must also double, because it's the same energy, it's just moving between different types. And if you wanted to, you could show that with an equation as well. This is a really tough exam question. You are likely to get at least one very tough exam question in your GCSEs. It's about, if you know it really well, that's great, you can make sure you get all 6 marks. If you're less sure on it, just making sure you pick up some of the marks. Again, this question's in your assessment, your assignment from today, so if you get to it and you can't quite remember what we just talked about, make sure you re-watch the video, go through the slides to remind yourself of the answer. Okay, thanks very much. Hope you're well. Bye-bye.